Welcome to the deep dive. Today we are really jumping in deep, exploring the huge shifts in how we understand the universe itself.
That's right. We're looking at how physicists, guided by some key insights, had to fight against centuries of, well, common sense thinking.
Yeah, we're tracing that journey from ancient ideas of a fixed cosmos all the way to, the much stranger reality of modern physics. Concepts like absolute space, absolute time.
Things that seemed obvious. Our mission today is to see how those ideas got dismantled piece by piece and what replaced them. It's really a story of unlearning as much as discovery.
Okay, so let's start at the beginning. The first big assumption to tackle. Where are we? For ages, the answer came from Aristotle.
And he wasn't just guessing. He had some pretty smart proofs that the Earth was a sphere.
Like the round shadow on the moon during an eclipse?
Exactly. And how when a ship sails away, you see the hull disappear first, then the sails. Good observations.
But the mistake wasn't the shape, it was the location, right?
Precisely. Aristotle and later Ptolemy put that sphere right at the center of everything. The geocentric model. Stars, planets, all circling us on these like perfect crystal spheres.
It sounds neat, but even then, there were hints it wasn't quite right. Didn't Ptolemy's math have a weird issue with the moon?
It did. To make the orbits work in his system, the moon sometimes had to be, mathematically speaking, twice as close to Earth as other times, which would mean it should look twice as big sometimes.
Which it clearly doesn't.
No. But the model stuck around for a long, long time. It wasn't just science, it fit culturally, too.
How so?
Well, the Christian church quite liked it. It put Earth, humanity at the center, and importantly, it left, plenty of room outside the outermost sphere of stars for heaven and hell, a tidy cosmic map.
Then came the shakeup. Copernicus, 16th century.
He suggested the sun was at the center, heliocentric. He actually circulated the idea anonymously at first, probably knowing it would cause trouble.
But it took Galileo and his telescope to really provide the knockout punch, didn't it?
Yeah, seeing moons orbiting Jupiter, that was huge. It showed plain as day that not everything orbited the Earth.
But Copernicus still thought the planets moved in perfect circles around the sun, right? And that didn't quite match observations either.
Correct. That's where Kepler came in. He was the one brave enough to ditch the circle, which everyone revered since the Greeks, for the ellipse, an elongated circle.
That feels like a massive conceptual leap, giving up on that perfect symmetry.
It was a real moment of unlearning. Nature isn't always as simple or perfect as we assume. Kepler described how the planets moved.
But not why. That was the next giant step. Newton, 1687.
Sir Isaac Newton. His universal law of gravitation explained why the orbits were ellipses. It was this force, gravity, depending on mass and distance. It connected apples falling from trees to planets orbiting the sun. All the same rules.
Okay, but here's where it gets really mind-bending conceptually, even with Newton. His own laws seem to undermine something he deeply believed in.
You mean absolute space?
Exactly. Newton's laws work the same whether you're standing still or moving at a constant speed. Like on a smoothly moving train, you can't do an experiment inside to prove you're moving, only relative to the ground outside.
Right. Which implies there's no absolute rest frame in the universe, no fixed backdrop against which everything truly moves, and this terrified Newton.
Why? Why was that so scary for him?
Because, well, philosophically and theologically, he felt space had to be absolute, like God's sensorium, an unchanging stage. Without it, motion felt unanchored.
I remember reading about Bishop Berkeley criticizing him on this.
Yes, Berkeley argued space and time might just be ideas in our minds. Dr. Johnson famously tried to refute Berkeley by kicking a large stone and saying, "I refute it thus," a rather physical argument.
Not exactly a mathematical proof.
Not quite. But Newton also saw a problem with his own gravity theory. He realized that if the universe was finite, gravity should make all the stars eventually clump together and collapse.
How did he solve that?
He reasoned, incorrectly it turns out, that if the universe was infinite and stars were spread out uniformly, the poles would balance and it could remain static.
The pitfalls of thinking about infinity.
Exactly. It shows even Newton struggled. Gravity in an infinite space doesn't automatically lead to stability.
Yeah.
Infinity often creates more problems than it solves in physics.
Okay, so we've sort of unlearned absolute position. The next pillar to fall was even more fundamental, absolute time. This takes us beyond Newton completely.
Right. And this part of the story hinges on the speed of light. For a long time, people assumed light traveled instantly.
Until
the Danish astronomer Ole Christensen Romer back in 1676. He was watching Jupiter's moons, timing when they disappeared behind Jupiter. He noticed the timing changed depending on whether Earth was closer to or farther from Jupiter in its orbit.
Because the light had further to travel.
Precisely. He figured out light had a finite speed. His estimate was about 140,000 miles per second, not bad for the 17th century.
Then James Clerk Maxwell enters the picture in 1865.
Maxwell unified electricity and magnetism, a monumental achievement. And his equations predicted that light was an electromagnetic wave traveling at a fixed speed.
A fixed speed.
Yeah.
Relative to what? That's the million-dollar question, isn't it?
Exactly. Physicists assume there must be some invisible medium filling all of space, the luminiferous ether that light waves traveled through. This ether would be the absolute reference frame.
The thing everything is moving relative to.
Yes, which led to the crucial experiment. Michelson and Morley, 1887. They tried to measure the Earth's speed through this supposed ether
How?
by sending beams of light in different directions, one in the direction of Earth's presumed motion through the ether, one perpendicular to it. If the ether existed, the light traveling with or against the ether wind should take a slightly different time than the light traveling across it.
And they found.
Nothing. Absolutely no difference. The speed of light was exactly the same no matter which way they pointed their apparatus, no matter how the Earth was moving.
Wow. So the ether just wasn't there.
It seemed not. The absolute frame of reference vanished. Light speed wasn't relative to some medium, it was just constant for everyone. This was a huge crisis.
Enter Albert Einstein, 1905, special relativity.
Einstein basically took the Michelson-Morley result at face value and built a whole new framework around it. He threw out the ether and the idea of absolute time.
What was his core idea?
Two main postulates. One, the laws of science are the same for all observers moving freely at constant velocity. Two, all those observers measure the same speed of light, regardless of their own motion or the motion of the light source.
And if you accept those two things, reality gets weird.
Very weird from a Newtonian perspective. Time itself becomes relative. If I'm moving very fast relative to you, my clock will appear to run slower than yours. Time stretches.
And space contracts too, right?
Yes, lengths in the direction of motion shrink. And perhaps most famously, mass and energy become interchangeable.
Yeah, mass is just a very concentrated form of energy.
That's it. And it also says a universal speed limit. Nothing with mass can ever reach the speed of light.
Why not?
Because as you approach light speed, your mass increases infinitely. It would take an infinite amount of energy to push you any faster. So space and time aren't separate things anymore. They're woven together into this four-dimensional fabric, space-time.
A truly radical unlearning. But even special relativity didn't explain everything. It handled motion, but not gravity.
Right. Einstein knew Newton's idea of gravity acting instantly across space couldn't be right if nothing travels faster than light, and if time itself is relative. That took another decade of intense work.
Leading to general relativity in 1915. Okay, let's try and unpack this one. This is maybe the biggest leap yet.
It really is. General relativity says gravity isn't a force pulling things across space. Instead, it's a feature of space-time itself.
How so?
Mass and energy actually warp or curve the fabric of space-time around them. Think of putting a bowling ball on a stretched rubber sheet. It creates a dip.
And if you roll a marble nearby, it curves towards the bowling ball.
Exactly. Not because the bowling ball is pulling it with some mysterious force, but because the marble is following the straightest possible path on the curved surface created by the bowling ball. That straightest path on a curved surface is called a geodesic.
So the Earth isn't being pulled by the sun, it's just following a straight path through the curved space-time the sun creates.
That's the essence of it. Gravity is geometry.
And this wasn't just a beautiful idea. It made specific, testable predictions that were different from Newton's theory.
Yes, tiny ones, but measurable. It correctly predicted a very slight wobble or precession in the orbit of Mercury that Newton's laws couldn't fully account for. About 1 degree every 10,000 years, but it matched perfectly.
And the famous one, light bending.
Right. If space-time is curved by mass, then light rays passing near a massive object, like the sun, should bend. Arthur Eddington controversially claimed to have confirmed this during a solar eclipse in 1919.
And this curvature of space-time affects time itself, too.
Yes. Time actually runs slower in stronger gravitational fields, closer to a massive object where space-time is more curved. This was confirmed experimentally. They put super-accurate atomic clocks at the bottom and top of a water tower in 1962.
And the clock at the bottom ran slower.
Just slightly, but measurably slower.
Mm-hmm.
And like you said, this is crucial for technology we use every day. GPS satellites are orbiting high up, where gravity is weaker.
So their clocks run faster than ours on the ground.
Exactly. If the GPS system didn't constantly correct for this time difference predicted by general relativity, your position calculation would drift off by several miles every single day. It's real, and it matters.
Okay, so Einstein gives us this dynamic picture of gravity as curved spacetime. But for a while, many people, including Einstein himself initially, still thought the universe as a whole was static, not expanding or contracting.
Yes, he even added a cosmological constant to his equations to force a static solution, something he later called his biggest blunder. That idea of a static universe died in 1929.
Thanks to Edwin Hubble.
Hubble was observing distant galaxies using the powerful Mount Wilson telescope. He noticed their light was shifted towards the red end of the spectrum, redshift.
Meaning they were moving away from us, like the pitch of an ambulance siren dropping as it moves away.
Precisely. And crucially, he found that the farther away a galaxy was, the faster it was moving away from us. The speed was proportional to the distance,
The universe is expanding.
undeniably. And if it's expanding now, then in the past, everything must have been closer together, if you run the clock backwards far enough.
You get to a point where everything was compressed into an incredibly tiny, incredibly dense state.
The Big Bang singularity, an origin point roughly 10 to 20 billion years ago. This brought the question of the universe's origin out of pure philosophy and into the realm of observational science.
It's interesting how even the Catholic Church in 1951 declared the Big Bang model compatible with the Bible, a shift from metaphysics to physics.
Indeed. Now, what about the future? Will the expansion go on forever?
That depends on how much stuff, mass, and energy there is in the universe, right? The average density.
Exactly. Alexander Friedman worked out the models based on general relativity. If the density is above a certain critical value, gravity will eventually win, halt the expansion, and pull everything back together in a big crunch.
And if it's below that value,
Then the expansion overcomes gravity and continues forever. The universe just gets colder, darker, emptier.
and current evidence suggests.
Overwhelmingly points towards eternal expansion. But even if it were to recollapse, that's likely trillions of years away. Long before that, our own sun will swell up and engulf the Earth in maybe 5 billion years or so. So, either way, humanity's long-term cosmic forecast isn't exactly rosy.
Okay, so we've shattered absolute space, absolute time, the static universe, what was left to challenge, predictability itself.
That's the final and perhaps most unsettling revolution. It goes back to an idea often associated with Laplace in the early 19th century, scientific determinism.
The idea that if you knew the exact position and speed of every single particle in the universe at one moment,
You could, in principle, use the laws of physics to calculate everything that would ever happen in the future and everything that had happened in the past. A clockwork universe.
but that dream died in the 20th century too.
It did, thanks to quantum mechanics. Werner Heisenberg's uncertainty principle, formulated around 1926, was the nail in the coffin for strict determinism.
What does it say, fundamentally?
It says there's a fundamental limit, imposed by nature itself through Planck's constant, to how precisely you can know certain pairs of properties of a particle at the same time. The classic example is position and momentum, or speed.
So the more accurately you measure where a particle is.
The less accurately you can possibly know how fast it's going, and vice versa. It's not just about having crude instruments, it's a built-in fuzziness in reality itself.
The universe is inherently probabilistic at its smallest scales. This is what made Einstein famously object, right? God does not play dice.
He really disliked the randomness implied by quantum mechanics. But experiment after experiment has confirmed its predictions. It's incredibly successful at describing the micro-world of atoms and particles.
So now we have these two incredibly successful theories. General relativity for the big stuff, gravity, the cosmos.
And quantum mechanics for the small stuff, particles, forces other than gravity. But here's the problem. They don't play nicely together. They're fundamentally incompatible.
Where does that incompatibility really bite?
At the extremes. In places where gravity is incredibly strong and things are happening on very small scales, like inside a black hole, or at the very moment of the Big Bang. General relativity predicts singularities there, points of infinite density and curvature, where the theory just breaks down and gives nonsense answers.
And quantum mechanics can't help because gravity isn't really part of its framework yet.
Exactly. So the biggest challenge in fundamental physics today is finding a theory that unifies them, a quantum theory of gravity.
And this search led Stephen Hawking, especially after a key conference at the Vatican in 1981, to propose something really mind-bending, the no-boundary proposal.
Right. Hawking and Jim Hartle explored what happens if you incorporate quantum ideas into the beginning of the universe, and crucially, if you use a mathematical trick involving imaginary time.
Imaginary time, like using the square root of -1.
Sort of, yeah. Mathematically, using imaginary time smooths out the singularity at the Big Bang. It makes the beginning of the universe look less like a sharp point and more like, well, like the North Pole on the surface of the Earth.
How so?
The surface of the Earth is finite in area, but it doesn't have an edge or a starting point, right? You can go north, you reach the North Pole, and then you just start going south. There's no boundary there.
So the idea is that space-time, maybe using this imaginary time concept, could be finite but have no boundary, no beginning edge or singularity.
That's the proposal, a self-contained universe. Finite in extent, but without a singular starting point in time.
Which has pretty profound philosophical implications.
Immense. If the universe has no boundary, no edge, no moment of creation, then what role is there for a creator to, as Newton might have thought, set things in motion? It suggests the universe just is, self-contained.
Wow. Okay, so summing up this incredible journey, we've gone from thinking space was a fixed stage and time an absolute clock,
To understanding space-time as a dynamic, curved fabric,
and from a deterministic clockwork universe.
to one that's fundamentally uncertain and probabilistic at its core. The quest now is to find that single unified theory, maybe a grand unified theory, GUT, maybe string theory, that can describe all forces, including gravity, within one quantum framework.
But testing these ideas is hard, right? The energies involved are enormous.
Astronomical. The Planck energy, where a quantum gravity effect should become obvious, is vastly beyond anything we can create in particle accelerators on Earth. So our best laboratory for testing these ideas is the very early universe itself, looking for feat signatures left over from that incredibly hot, dense state.
So we've traced this arc of understanding, how the universe began, how it works. Let's leave our listeners with one final thought to chew on, something that connects back to our everyday experience. The arrow of time.
Ah, yes. Why does time seem to flow in only one direction? Why do we remember the past but not the future? This is the psychological arrow of time.
And physics links this to something called the thermodynamic arrow of time.
Exactly. That's the observation that in any closed system, disorder, or what physicists call entropy, always tends to increase. Your organized room gets messy, your hot coffee gets cold, things run down.
They don't spontaneously get more ordered.
Never. The no-boundary proposal we mentioned suggests the universe started in a very smooth, ordered state near its beginning. This initial low entropy state is what allows entropy to increase as the universe expands, creating the thermodynamic arrow of time that we experience.
So here's the really provocative thought. Why do we find ourselves living now in this expanding phase where disorder is always increasing?
Consider this. Intelligent life, like us, is incredibly complex and ordered. To maintain that order, to think, to live, we have to constantly consume ordered energy, like the chemical energy in food, and convert it into disordered energy, mostly heat. We are entropy-producing machines.
So we can only exist in a universe, or at least a phase of the universe, where there is a strong thermodynamic arrow, where disorder is increasing.
It seems likely. The increase in disorder, the arrow of time driven by the universe's expansion from an ordered state, might be a fundamental prerequisite for the existence of beings complex enough to ask these questions in the first place. We exist because the universe is running down.